Okay, welcome back, everybody, for our second session of the verification mentoring workshop. So we've had two mentoring talks this morning, two exciting talks, and now we're switching gears for this second session. And we're very excited to have a technical talk from Eva Darulova. Eva is currently tenure track at the Max Planck Institute for Software Systems. Before that, she was a PhD student at EPFL, where she was advised by Victor Kunchak. And she works on programming languages, software verification, and especially with a focus on approximate computing and numerical programs. And she will talk to us today about analyzing and optimizing finite precision programs. You have the floor, Eva.
Thank you for the introduction. So let me share my screen. So can you see my screen? Okay.
Yes, I can see your screen.
Okay, great. All right, so welcome to this session. As Jean-Baptiste said, this is going to be a technical talk. So I'll be talking about some very concrete problems on finite precision programs. And hopefully this will give you a bit of a flavor of what kind of problems arise in this domain, and that finite precision is not quite as scary as many people may think. And hopefully I will also give you some idea of how a research agenda can develop over time. Because when I started this research direction, I certainly did not expect it to work or continue as it did in the end. So what I'll do is, let me go back. So I'll start with some basic background on finite precision, so floating point and fixed point arithmetic. Then I will explain at a very high level what kind of analyses we can do to get a bit of a better handle on the issues that arise, and then how we can use these to actually optimize numerical programs. I'll keep this talk at a very high level, so I'll try to explain everything basically by example. And I'll post some additional references at the bottom for people who are interested in a more deeper view on the topic. But before I go to the technical part, let me say a bit more about myself and where I come from. So as the name may suggest, I'm originally from Eastern Europe. I was born in Slovakia, but I grew up mostly in Germany in a small town called Jülich. After high school, I decided I needed to do something else and see something else. So I did my undergrad at University College Dublin in Ireland. After my bachelor's, I first thought, well, should I stay in research? Then I've seen a very interesting talk on verification at the university. So I decided I need to know a bit more. So I'll follow up with a PhD, which I did at EPFL in Switzerland. And after that, I've started a tenure track position at the Max Planck Institute for Software Systems back in Germany. So when I left Germany at 18, I did not actually think I would come back so close to it in the end. All right, let's start with finite precision. And so this is something that many of you may be familiar with. What you originally want to compute, say 0.1 plus 0.2, and well, this looks easy, right? That's 0.3. When you type that into your computer, you may get something like this, and it's quickly obvious that this is not quite 0.3. And at this point, the reaction of many people seemed to be, well, this is just nonsense. And XKCD actually seems to agree. So there was recently this comic that essentially talks about finite precision numbers, and at some point you only get garbage, and then you continue computing with garbage, etc. So to some extent, this comic is actually quite true, but hopefully I'll convince you in this talk that it's not always quite so bad, and with the right techniques and tools, we can actually do something useful with finite precision. All right, you may ask, well, why do we even want to use finite precision when it gives us some odd results like this? So why not just compute with infinite precision? And then you may quickly run into issues. For instance, when you try to compute 1/3, and try to print this in decimal. So in the real valued sense, you would have an infinite set of decimal digits, which obviously on a finite digital computer that we have today, we cannot represent. So in this sense, it's actually nice that the computer will cut off the 3s at some point so that we can actually get some result at all. Well, you may say there are other options than just writing down an infinite number of digits. Why even try to expand this into a decimal notation? Why don't we just keep the 1/3 as a 1/3? So for instance, if you have some software support, you may represent this as a rational, and in this way represent it exactly. So this is indeed possible. You can do this. However, this comes at a cost. So once you start evaluating some large computations, for instance, some neural network, you will very quickly come into performance problems. If you take something like a rational representation, this is usually implemented using some big integers that tend to grow relatively quickly as your computation progresses and just will take more and more amount of time. So basically what we get with finite precision is 1 point on a trade-off between efficiency and accuracy. So on one hand, we have the completely accurate representations such as a version of reals that is actually computable or rationals. On the other hand, we have finite precision arithmetic such as floating point or fixed point that I will explain in some more detail later in this talk. And there's also something in between, which is usually called arbitrary precision, which is in the end, it's finite precision, but it has a lot more bits available than your usual floating point arithmetic. So I'll focus mostly on floating point and fixed points, and they are important for many applications in practice because they provide the necessary efficiency. Now they do introduce some errors, as you have seen on the previous slides, but the point is that for many applications, this error is tolerable. But let's see where that error really comes from, and let's take a really basic. So let's start from the beginning. So one of the most common finite precision representations is IEEE floating point arithmetic that's standardized by the IEEE 754 standard. And the most common number format is the binary floating point number that is represented as a triple. So consists of a sign bit, a mantissa or a significand, and an exponent. Now in this representation, the significand provides us with the precision. So those are the actual digits that we have. And the exponent gives us a range of numbers. So there are several standard formats that most of you are probably familiar with. The floats, so single precision and double precision, that have a different number of bits available for both the significand and the exponent. So the more bits you have available, the larger range or the more digits you have to represent the number. Now the IEEE floating point arithmetic comes with some special values that can cause a certain amount of headaches as well. But there's also a point where they can be useful. So for instance, if you divide some number that is not 0 by 0, you will get an infinity. If you divide 0 by 0, you'll get a not a number because that is a mathematically ill-defined value. So similarly, taking a square root of a negative number mathematically doesn't make much sense. So you will get a not a number. In addition, these cause some additional trouble because not a number is not equal to itself for some reason. So you have to be actually very careful how you write your code. So you're not taking the wrong branch. But we'll also talk later in how to make sure with a static analysis that these values, for instance, do not occur in your computation. So you can be sure that whatever you compute are actual real numbers. So one effect that we have seen on basically the first slide was the rounding. So because we have only a finite number of digits available, every arithmetic operation has to be rounded, and the standard mandates that they are correctly rounded. So we have some idea of how the rounding works. And basically what the standard says is that every operation has to be rounded, or the result has to be as if it was performed in infinite precision and then rounded according to one of the different rounding modes. So the default one for most programming languages is just rounding to nearest. There's different ways of dealing with ties. You also have rounding to 0 or to plus and minus infinity, which are important for certain applications. But we'll just assume rounding to nearest. So basically every arithmetic operation has to be rounded, but you know exactly how the rounding looks like, and especially you know how big the rounding error for each arithmetic operation is going to be. Now, a particular, perhaps somewhat annoying aspect of floating point, or in general finite precision arithmetic, is that it does not support many of the usual real valued identities. So it is commutative, but it is not dissociative or distributive. We will actually leverage these particular non-identities a bit later in the talk. So floating point arithmetic is commonly used on, say, a laptop. However, when you have an embedded system, the floating point unit that you usually have as a hardware may be just too expensive. It may take too much energy or too much space on your chip. So what you may want to do is use fixed point arithmetic for your numerical computation, which can be implemented with just integers. So this is in particular interesting when you have FPGAs or ASICs where you want to run your computation. And it also provides you a little bit more flexibility because it allows you to have more varied formats, not just 32 and 64 bits formats, but you can have anything in between. So most people may not be familiar with this, so I'll try to briefly explain how numbers are represented and also what is the catch. So first, every number is represented as a bit vector, of which some of the bits are represented or are called the integer bits. They represent the integer part of a variable's value, and the other bits are the fractional bits. So for instance, if we have the value 3.14, then the orange bits would be used to represent the 3, and the green bits would be used to represent the 0.14 to some accuracy. In general, we want to make sure that we do not have overflow, so we want to make sure we have enough integer bits so we can represent all the possible values that X will ever attain in a program or in a computation. And then the remaining bits that are still left over, those we will use for the actual accuracy of the decimal part. Now, this decimal point is implicit in the sense that it is not actually encoded in the format. The value consists of just the integer bits. So it's only us when we design the program that we know where this decimal point is going to be. And this is sort of the catch. So we can use just integer circuits, but we have to do a bit more work and compile time to actually do the computation. And essentially what we need to determine is where these implicit decimal points are. And I now want to explain you with a small example why this is important and why this is the case. So suppose we have now X and Y, two values, and we want to add them. And Y uses 4 bits for the integer part instead of 5. So if we just want to use regular integer addition, what we need to do is we need to align these according to the implicit decimal points so that we are adding up the right numbers together. And for this, we need to determine where that implicit decimal point is. Now, in order to do this, we need to know what are the possible values of X and Y so that we reserve enough bits for the integer part so that we don't get overflow. And later on, we'll see an analysis that will give us exactly this information. Now, similar to floating point arithmetic, in addition to this compilation issue, arithmetic operations incur rounding errors just as floating point arithmetic. So this is something that we may want to deal with. All right, so hopefully now you have a bit of an overview of what I'm talking about when I say finite precision programs. And now let's see what analysis we can do to help, say, both the compilation and with dealing with the rounding errors. So you may ask, well, why do we need to deal with the rounding errors? How bad can they possibly be? So sometimes I have the impression when talking about finite precision, some people have the attitude that, well, this is just real numbers and we'll just ignore all of the rounding errors. And others will say, oh, they're so bad, let's just not use floating points at all. Now, I think the truth is somewhere in the middle for most applications. So a finite precision is indeed good enough if we make sure that we have some control over how large the rounding errors are. Now, before going into this snippet of the XKCD comic again, I want to fix some of the notation here. So I want to make a distinction between accuracy versus precision, because that's going to be important. So we're actually going to talk about the accuracy of numbers, where accuracy means the difference to the ideal value. So that's the difference to the value that we have really wanted to compute if we had infinite precision. And the precision is really just the number of bits, more or less, that we have available physically. So in this setting now, the XKCD comic says that if we add two accurate numbers, we get a slightly less accurate number. And really just before I get there, an example to make the difference between accuracy and precision clear. If the target value that we wanted to compute was 4.2, 4.5 would be more accurate than 4.789, but 4.789 would be more precise because it has more bits essentially available to represent the number. All right, so now let's go back to the adding two accurate numbers and getting a slightly less accurate number. The crucial question really is, how much less accurate is that number? And is it still sufficient for my application? Now, the question of whether an accuracy is sufficient for a particular program is really application dependent. So this is something that an engineer will have to tell us. But then we should use static analysis to determine this. Well, before we go to the static analysis, I want to give you some brief idea of how we could use a dynamic analysis, because I think this is going to make a few things clear down the line. So if we just want to do some testing to get an idea of how large the round of errors can be, what we can do is we take our a version of the program. So I'll call this the low precision version. So for instance, this could be a single 32-bit precision floating point arithmetic. And we'll run it side by side with a high precision version. And then we'll compare the results and see in how much they differ. Now then, we can do this. Before we can measure rounding errors, we have to define how we're actually going to measure them. One way to do this is to use the absolute error metric. So we will just compare the real valued or ideal or high precision version to its low precision, finite precision version, and we'll just take the absolute value of this. So on a very, very simple example, suppose we're adding two numbers, and we're just going to run this small function with two inputs where x1 is going to be 0.1 and x2 is going to be 0.2. Now I'm here using the double floating point arithmetic as the high precision version, just because it was easier to implement and to show. And we're comparing it to the result that we would have gotten in the single 32-bit floating point version. And you can see that we actually get a number. And in this case, this is probably going to be relatively accurate. Now, in practice, you would run this with a much higher precision, so maybe 500 bits, to be sure that you are not running into some weird corner cases. Another possible metric besides absolute error is relative error, which gives us the error in relation to the actual value that we're computing. Now, this may be more appropriate as a measure because, say, you have an error of 0.1. Whether or not that error is large depends on what the value is that you've actually computed. If the value that you've computed is 0.1 itself, then you basically don't know what your result is really going to be, because your result could be anywhere between 0 and 0.2. If the value that you've computed, on the other hand, was on the order of, say, 10,000, then that error is indeed small and may be appropriate for your application. So if we do our very simple calculation with the same inputs here, then we can indeed also compute the relative error. And what you can then do is repeat this process repeatedly with different inputs to get some idea of how large the round of errors actually are in your computation. Now, to many people, it may now be obvious what the drawback of this approach is. For instance, in our example here, we only know the rounding error for 0.1 and 0.2. And in practice, there are too many finite precision values, so you cannot exhaustively do testing. So what we instead want to do is a static analysis. So we want to compute a worst case error bound for a set of inputs without actually running the previous approach on all of the possible inputs. We want this error bound to be sound, so it to be a guaranteed error bound, so that indeed it is, so no actual round of error in practice can be bigger than whatever we compute. Now we're going to focus on the absolute error here. And as I said, we're going to maximize this entity for a set of inputs. For example, for our addition, we may say we're interested in inputs between roughly minus pi and 0 and 42. What these bounds are, that again depends on the application. So for example, if you have an embedded system, then you may know the range of your possible inputs that may come from sensors, and that would be the bounds that you would input here. Now, I said we're going to talk about static analysis for absolute errors because relative errors turn out to be a bit more complicated, essentially because we have a division and we may have to deal with a division by 0 errors. If you're interested in what you can do about relative errors, at the bottom there is a paper that may be interesting. All right, before we go to our rounding error analysis, let's look at a somewhat simpler problem that I've advertised before. We want to show that infinity and none do not occur in a program for a particular set of inputs. And this information, as I also mentioned before, is needed to do the compilation for fixed point arithmetic. We need to know what are the ranges of all the possible variables in a program. So for example, if we have now an actual embedded controller, so this is a controller that supposedly controls a rigid body that I haven't developed myself. I've taken this from someone else's work. And there, the inputs may come from a range from minus 15 to 15. What we want to compute is that the possible result of the finite precision implementation of this function is between minus 705.1 in this case and plus 705.1. Now, this 705 now is just a magic number. So this is very difficult in general to get manually. So that's why we want to have both an automatic approach. So we can just have an analysis that will automatically give us this result, but the analysis should also be accurate. In the end, we could have, we could always return a range from minus infinity to infinity. It will be sound because all of the possible values are included, but it will be essentially useless. So the way we're going to do this range analysis is we will first define an abstract domain that will allow us to represent a set of program values. So we don't have to execute the program on each concrete individual value individually. And then in the second step, we will define transfer functions that will define how these abstract elements that represent the program values propagate throughout the program. So we'll essentially execute the program abstractly on just the individual abstract domains and not on individual program inputs. The abstract,
if I may interrupt just for a minute, I have some questions on Slido about elaborating on soundness. Like, what do you mean by sound? People would like to know.
Okay, so what I mean by sound is that the result that we compute captures all the possible concrete executions. So in the case of range analysis, maybe I can go back. Go back here. It means that if I pick any value for x1, x2, and x3 that is within the minus 15 and 15 bound, the result of evaluating the function f is guaranteed to not be outside of the range that I have computed. So it will definitely be within minus 705 and 705. I hope this answers the question. And for rounding errors, it means that there does not exist a concrete execution that would have a rounding error that is bigger than the bound that our analysis computes. So it's a guaranteed upper bound. All right, so we want to compute, so we want to develop an abstract domain, and we'll use one that is actually relatively well known and has been well known for a while. Oh, right. Before I go to the abstract domain, for those who are familiar with abstract interpretation and data flow analysis, you may say, well, wait, this is not quite enough for programs. So indeed, this is enough to handle only straight line code. I will talk a little bit about loops and conditionals later. They turn out to be tricky for finite precision programs, and I'll try to explain why later. So for now, we're focusing just on straight line arithmetic expressions here. And for those, we will use intervals. There are some more complicated abstract domains that I will also sketch on later, but I want to stick to intervals because I think they're easy enough to present in the setting. So an interval represents a set of values by a lower bound and an upper bound, and it represents all of the values that are in between. So this is relatively easy. Then we need to define the transfer functions, which in this setting means that we need to define how to do arithmetic on intervals. And for soundness, so in order to guarantee that all of the possible results are included in the results, we need to make sure that when we do the arithmetic, we enclose all the possible results of taking the arguments x and y from their respective input domains. So this is a very general formula that's not particularly enlightening and helpful. For the individual arithmetic operations, you can define simpler formulas, I guess. I'll just show you or demonstrate how this works on an example because I think that's the simplest in this case. So say we have x1 that is between -1 and 3, and x2 that is between 0 and 4. If we want to add x1 and x2, then it's probably quite intuitive to most of you that the smallest possible value that we could get would be -1 in this addition. So we will take the smallest possible value that x1 can get and the smallest possible value of x2, and we will get -1. To get the upper bound, we would take the biggest possible value of x1 and the biggest possible value of x2, and we would get 7. If we do multiplication, this is a little bit more tricky. So we have to consider what is the smallest possible number we could get. And in this case, we would get it by taking the negative -1 and multiply the biggest value of x2, so 4. So we would get -4. So that's the biggest, so that's the smallest number or the biggest negative number that we could get. Now, similarly, the largest number we could get is now, again, just taking the upper bounds on x1 and x2. So this is, for now, assuming real arithmetic. So in this case, we're not dealing with the round of errors yet. So now we know how to compute with intervals. So now let's actually move to rounding errors. And we will extend the abstract domain that we had now for just computing the ranges of individual values to also compute an error bound. So as a reminder, what we are after is the worst case error bound that's given by the expression here, maximized over some input domain. So we'll again define an abstract domain, and then we'll define transfer functions for how to execute the program abstractly with these. Now, the abstract domain is going to be a little bit more complicated in this case. It will be a tuple of intervals. So we will have 2 intervals that will represent the possible values of every variable. The first interval will capture the real valued range. So those are all the possible values that we could get if we were executing our real valued function. So that's the function f. So this is as if we were executing our program in infinite precision. And then the second tuple captures the error that we will get in the finite precision program with respect to its real valued counterpart. Now, in this case, the intervals, as is shown here, are symmetric. So there will always be minus e to e. So in principle, we could just keep track of e, but I think for the presentation, it's easier to just keep everything to intervals. So just to illustrate this, if we have a number line, the real valued value x is going to be guaranteed to be between a and b. And then what we're going to measure is the difference between some value x and its floating point version that would actually happen that we would actually compute in a program. And what we want to compute is the maximum distance that the floating point or finite precision version of x could have to its ideal value. Now, these could be in between, so the floating point or finite precision value could be in between a and b, but it could also happen that the finite precision value would actually lie outside of a and b. So this is also captured by our abstract domain. What that second term in the tuple really represents is just the difference between the two. So where does this error actually come from? For floating point arithmetic, we'll use the IEEE 754 standard, which actually defines the error bound for individual operations. If we assume correct rounding and if we assume rounding to nearest, then an individual rounding error for some arithmetic operation is given by this formula. So basically we have, say, x plus y, that's our, oh, there's a equality too much. And so if x plus y is our actual real valued result, then the error is going to be the magnitude of x plus y times some small error that is bounded by the machine epsilon. So this is a value that's given that is different for different finite precisions. So we also see here, so basically the second term, that's the absolute error. That's the one that we want to capture. And here you also see that this absolute error depends on the range, which is why we're also keeping track of the range in our abstract domain. Similarly, for input values, they also may not be representable in binary, so we'll have a similar expression. So we take the magnitude of x, multiply it with the machine epsilon in this case to get an absolute error bound. Now for fixed point arithmetic, the situation is similar. So the error depends on the actual fixed point format. So it depends on how many bits we have and how many fractional bits we have, but it's essentially more or less the same thing. So now we know how to get one round of error. Now we need to also figure out how to actually propagate them. So if we have committed some rounding error and then we continue with our computation, how do these errors combine and possibly magnify? So we'll actually derive this because I think this is quite enlightening also and relatively straightforward. So let's look at addition and let's look how to add two finite precision numbers, x and y. We can write them as the real valued x plus some error and the real valued y plus some error. Now, if we do some small rearrangement, we'll get x plus y. So that's just the real value, the ideal value we would have gotten if we had infinite precision. And then the second, so the second part, that's the error. So we essentially just need to add up the errors for addition. That's the short version. So if we want to write this a little bit more formally, if we want to write down our transfer function for the abstract domain, what we will do is we will add up the ranges using interval arithmetic. We will add up the errors as we have just derived, and we will add the new round of error using the formula from the previous slide. So if we have multiplication.
Just a quick clarification. Someone is asking, in what arithmetic are you performing the transfer function operations? I mean, I feel like you're going over it, but maybe clarifying in what arithmetic you're performing the transfer function operation.
So what you're actually computing is the bottom part here. So it's and the capital letters represent intervals. So the arithmetic is actually done in interval arithmetic. So the R's and the E's, they're all intervals. And then the addition is done as interval arithmetic. And one perhaps additional thing, in our actual implementation, at least in our tool, you could possibly do it differently. The intervals are represented with rationals or some exact arithmetic so that we do not internally have to deal with rounding errors. So if we were actually computing with floating point errors in our analysis, we would also have to make sure that our analysis is capturing that internal rounding error as well. We can get around that by representing the intervals with rational lower and upper bounds so that the actual internal computation of the analysis are correct and exact without any rounding. Okay, so for the, so that was addition. Multiplication is a little bit more complex. We'll do the same trick. We'll take the floating point version or finite precision version of x and y as the real value plus some error. If we multiply this out, we will again get the first part, that's our real ideal value, and then the second part, that's the error. And from this, we can then again derive our transfer function, where we will do multiplication on the range intervals. And then we will do the error propagation. And here again, we're doing all of the operation on intervals, which is why I said initially it's easier to also keep the error as an interval, because now here we can multiply the interval that represents the range with the interval that represents the error. So all of this is well typed, and then we'll also represent the new error as an interval. So that's basically already it. That's what we need to compute a sound upper bound on rounding errors. We have, this is already something I have done during my PhD, and now this is implemented in a tool called DAISY that we're continuing to develop. It has a particular input format where you can write the function that we have seen before as a actual function. You can provide the input bounds, and then you can compute the worst case errors using the analysis I've just presented. So for instance, we see that if we choose double floating point precision, we get an error of 10 on the order of 10 to the minus 13. If we use single precision, the error is much, much bigger. So this may be useful to decide whether you could potentially use a lower precision or not. Something that many people may find interesting is if we use fixed point arithmetic and we use 32 bits. So basically we use the same number of bits as for the floating point single precision version. The error is actually 2 orders of magnitude smaller. So this may be one more reason for why you may want to use fixed point arithmetic. And the reason for this difference in error is that in the fixed point arithmetic, you are kind of using all of the bits that you have to a maximum. So there are no bits that are essentially unused because you decide how many bits you use for the integer part and how many bits you have left for the fractional part. Whereas in floating point arithmetic, there is a fixed number of bits that are reserved for the exponent. And the exponent is chosen such that you may be potentially representing some huge numbers that may not, for instance, show up in an application like this embedded controller. Now you could try to use some other bit length for fixed point arithmetic, and our tool would, for instance, tell you that 16 bits is not enough because you may have an overflow, so the number of bits you have is not enough to represent the integer part. So
I have one question here, if this is a good time. So Mohit asks, in your analysis, do you store the real addition and multiplication, like the exact, I guess, real addition and multiplication? And if so, how do you sort?
No, so we do not actually perform any concrete execution of the program. So we only ever do computations over intervals. So we only represent the range of x1, x2, and x3, and then we'll do the addition and the multiplication over the intervals. And the intervals themselves are represented with, in our implementation, with rational numbers. So the computation of the interval bounds, the lower and upper bounds, they will be done with rational arithmetic. So with the big integers, etc. So we do not actually compute any concrete value of the ideal real valued program. All right, so what I have shown you so far is the most simple abstract domain that you can use, but it is actually quite effective for many applications. But for some, it may not be accurate enough. So this is a well-known problem in interval arithmetic. If you compute x minus x, you don't actually get 0, but you get an interval that is twice as large as the one that you started with. And the reason for this is that if you just have an interval, you do not actually know whether the numbers correspond to the same value. So you have to assume that they correspond to possibly different values, and you just have to compute the larger interval. So in short, interval arithmetic does not track any correlations between your variables. So this also suggests a more accurate abstract domain would be one that keeps track of linear correlations, and this would be affine arithmetic, or sometimes also called zonotopes. That would, for instance, in this case, compute the result of x minus x as 0. Now, obviously, this comes at a cost, so you may the actual analysis is going to take longer. I will not go into details because I think this would be too much for this talk. But if you're interested, there are some other domains. Alternatively, you can take a completely different approach. So instead of doing a data flow analysis, as what I have just presented, you can actually try to solve the absolute error as an optimization problem. So it's even formulated as such. You're maximizing the error over an input domain, and you can literally just write that as an optimization problem. To make it tractable, you will have to do some approximations. So we'll again introduce some abstractions and some over approximations. So this is not my work, this is someone else's work. This can be more accurate for floating point arithmetic, but unfortunately the approach does not work for fixed point arithmetic. So basically there's no free lunch, but depending on your application, one method or the other may be better. Now, conditionals can be tricky because what may happen is that your ideal computation, the real valued one, can, for instance, take the if branch of a conditional statement, and your finite precision version, because of the error it has committed, may take the else branch. So if you want to soundly compute an upper bound on the error of the program's results, you have to take into account this divergence, and you have to take into account that you will potentially compute vastly different results. Now, in practice, it is not enough to just say, well, if this divergence can happen, then you issue a warning or you give up, because as soon as you have finite precision, you will always have an error. So you will always have some values that would take a different branch. So what you really want to make sure is, even if you take the different branch, the error is still not going to be too large. So you're still not going to be too off. There are some approaches to compute this. Again, I think these are a bit too much for this talk, just basically based on their complexity, but just that you know there are techniques to handle this as well. And finally, loops. So what you normally would do is compute a loop invariant. So you would compute some expression that would capture, in this case, the error as it would hold for every loop iteration. This is unfortunately not possible as easily because round of errors in general keep growing with every loop iteration. So just keep bigger and bigger and bigger. So you can't just write down one expression that would capture all of the errors for all of the loop iterations. All right, but despite all the limitations of the analysis that we have seen so far, it's already enough to optimize some interesting small programs, but still programs that do appear in practice, for instance, in embedded systems. And let me now show you two optimizations that I've developed mostly, in exactly the order that I'm going to present them. So the first one is based on the fact that finite precision arithmetic is neither associative nor distributive. So it doesn't, for instance, satisfy this equality. So this also means that for the rounding error analysis that we have seen previously, we always have to make sure that the program is actually executed in exactly the same order that we have, for which we have run the analysis. Otherwise, our round of errors would not be valid anymore. This also means that depending on how we reorder our computation, the rounding errors will be different. And for some, it will be smaller, and for some reorderings, they will be bigger. So the idea we had was, well, let's actually leverage this, and let's try to find an order of computation that has a smaller error than what you may start with. And if we can do this statically, so if we can do this in compile time, we will do our effort and our search once, and then at runtime, you will always be able to run your application with a smaller rounding error. Now, it turns out that the problem of finding the optimal evaluation order is NP hard. So basically, we cannot hope to, basically, it means if we wanted to find the optimal order, we would have to go through all of the possible rewritings, and there are too many to do that. So we'll do a heuristic search. But we will use our static analysis from before. So we will always have a guarantee on the rounding error. We won't have a guarantee that we have found the best evaluation order, but we will know that the errors won't be bigger than what our analysis says. And the heuristic search that we will use, or that we have found to be actually very effective, was a genetic algorithm. And when I took a course in genetic algorithms in my undergrad, I never thought I would ever use this ever again. But it turns out that for this particular application, it was better than anything else we have tried. So you never know what the knowledge will be useful for that you have gained. The way it works is, so genetic algorithms are inspired by evolution. So we will have a population that we will evolve through a number of iterations. And we will initialize this population with just a copy of the expression that we have. So I'm here showing just 4. In practice, we will have more than that. But just so we keep this manageable. Then we do this evaluation, evolution of expressions based on their fitness. So usually the fitter an expression or an individual is, the more likely that individual is to reproduce in the theory of evolution, and we'll do a similar principle here. So the smaller a rounding error is, the fitter an expression is, and the more likely it is to continue being in our population. And we will use our static error analysis to compute the rounding error. So since we started with all the same expressions, the errors are all the same initially. And then we'll do the evolution of our expressions by mutating them. So we will pick some sub-expression and we will apply some real valued identity to it, and we will rewrite it. This will change the rounding error. So for instance, here it would get smaller. Now we would hope to find some rewritings that would make the error hopefully smaller. And we'll repeat this for more of our expressions. So we will find a variety of different orders of evaluation with different fitness, so with different errors. And the trick in the search is that in each iteration of our algorithm, we will pick the next expressions that we want to mutate based on their fitness. So this means that the expressions that already have a smaller error are going to be more likely to be mutated again and hopefully have an even smaller error. But it also allows, with a certain probability, that even the expressions that were actually pretty bad can still go on and get mutated. And this helps us to get, avoid local optima in our search. All right, that was the first optimization. The second one was based on the realization that before we have always assumed that all of the operations are implemented in exactly the same precision, but we don't actually have to do this. So why this is useful, for instance, if we have here our rigid body controller again, and suppose now the user has actually specified that for their application, the error cannot be bigger than 1.75 to the 10 to the minus 13. This is a random number for now. So if we implement this function in double precision, our analysis at least is not able to prove that the rounding error is going to remain below this error bound, but it's just not enough. So if the error was just a little bit smaller, then we would meet the error bound. Now, if you only consider uniform precision, then we would have to basically move all of the operations to the higher precision. And in this case, this would be something like a quad. So this would be a software implemented floating point type that would have double the precision of a double precision. Now this would satisfy the error bound by a huge margin. So we are now orders of magnitude more accurate than we need to be. And it would also be significantly slower than the double precision version. So what we really would like to do, since we're just not meeting the error bound, is to use a mixed precision. For instance, we can put 3 arithmetic operations in double precision, and we can do 4 in the more accurate quad precision, and this is going to satisfy that error bound that we want, and it's going to be already significantly faster than the uniform quad precision version. Now I'm showing this here for 2 particular floating point precisions. Now the same principle works for any combination of finite precisions, including for fixed point arithmetic. So there you can also want to have some operations, say with 16 bits and others with 17 and maybe 18. Now again, it's a little bit too much to ask of a user to figure out what is the particular assignment of precisions to arithmetic operations, because this is very unintuitive. So we'll again do a heuristic or an incomplete search, and we'll again use our static error analysis to get guaranteed error bounds. And I'll try to show you our algorithm for this. Just a note before, we have tried to use the genetic algorithm that we had used for the rewriting, but at least for floating point arithmetic, it seems that it's just completely not working. We are now retrying this for the fixed point arithmetic at least, and it seems to be a bit better. But at least for floating points, the following algorithm turned out to work much better. So what we will do is we will represent all of the arithmetic operations in a list. So a box is a list of all arithmetic operations, and quad means that all of the arithmetic operations are performed in quad precision. We will run our static error analysis with this setting, and it will hopefully tell us that it meets the error bound so that we have a hope of finding some lower precision. Then we will try to lower all of the operations to the next lower precision, which in this case is double. Here, our static error analysis will tell us the error bound is not met. So what we'll now do is we will split the arithmetic operations, and we will put some of them in double and some of them in quad precision. And then we'll again check. Suppose that in this example, the error bound is still not met. We will continue our splitting until eventually we will find some setting where the error bound is met. And then we still have to decide, if we have several candidates, which one we want to pick. And we will do this based on a cost function that would measure, for instance, performance, so that we get the fastest program. All right, so I discussed 2 optimizations. They seem to be somewhat unrelated. So you have rewriting that can improve your rounding error. Then you have mixed precision that will improve your performance. Well, it turns out they're not quite as unrelated, because you can combine them and improve performance even more. So the way this works is the rewriting will reduce the error, which gives us a little bit more leeway to apply maybe more lower precision arithmetic operations. And for the example that we had before, we can now perform 4 instead of 3 arithmetic operations in doubles, and then 3 in quads, which means that we now improved the running time over the uniform quad precision by 43%. All right, that brings me already at the end of my talk. I hope I have given you some glimpse of what you can do with finite precision programs, and that with all of these techniques and tools, it's actually not quite so bad. So we have really aimed for some fully automated techniques, but what I have discussed today is really only a glimpse of what is there. The research area is still very much research in progress, and there are many different techniques that are being developed by also many different groups. So at the bottom, you can see some more work from my website and from the FP Bench community page. So FP Bench is a community effort to collect benchmarks and to collect a list of different techniques. For instance, you may find some smarter dynamic analyses than what I have shown today that will do a guided search to find inputs that cause large errors. This is in particular helpful when, for instance, our static analysis says that the error bound is not met. Our analysis won't tell you what are some particular concrete inputs that may actually be helpful for debugging. Similarly, you can use a dynamic analysis-based mixed precision tuning that will scale to larger programs than our static analysis can. There is work that verifies floating point compiler optimizations. So GCC, Clang, and now also some verified compilers, they do optimize floating points, and you also want to make sure that those optimizations are correct. And some very recent work has also looked at not just optimizing arithmetic operations, but also transcendental functions. So for instance, sine and cosine, so that you get a little bit more choice in your precision, not just single and double floating point arithmetic. And with that, I thank you for your attention, and I'm happy to answer any questions.
Thank you so much, Eva, for this talk. There are a bunch of questions on Slido. I'll ask the most upvoted ones. If you want to have yours asked, please upvote it. So Saptarshi asks, more from the beginning of the talk, are precision-related behaviors like commutativity, the fact that commutativity is preserved but associativity is not, are they documented in somewhere in the documentation of the language or the library? Do you have examples of links? Are they documented or not really?
So the fact that it's commutative is probably documented in the IEEE standards. That it is not associative and distributive, that simply follows from the fact that you have to do rounding. Because the rounding will depend in particular on the magnitude of your variables, and they will be different depending on your evaluation order.
Okay. Are there other behaviors you can think of that you didn't mention before that are of interest?
Well, the nans and infinities, those can be tricky. For instance, when you think about compiler optimizations. So for compiler optimizations, GCC and Clang have a fast math flag that will make your numerical programs a lot faster, but they will violate some of the IEEE standards rules, essentially. For example, they may remove some of the checks for whether you have a not a number. As I mentioned, not a number is not equal to itself. And if you specify the fast math flag, then the compiler will just assume that you know for sure that you do not have a nan, so you do not have to check for this especially. So there are some tricky behaviors that you want to get right that are really unintuitive because it doesn't follow the real arithmetic rules that we're familiar with.
Okay, so thanks. One other question from Mohit is, in your genetic algorithm, what do you choose as the fitness function in a genetic algorithm? And what's the threshold? Like, you know, what do you choose to evaluate the fitness of each candidate, basically?
So we use our static error function. So basically the fitness is equal to the rounding error that you have for that particular expression. Now, this means that we're optimizing for the expression for which we can prove a smaller rounding error, not necessarily for the program that actually in practice has the smaller rounding error. So it could be that our analysis thinks that one expression has a larger rounding error just because of the over approximations that the analysis performs, when in fact it would have a smaller rounding error than another expression. But in practice, if you want to have soundness guarantees, what you care about is the error that you can prove, not the one that actually exists.
Okay, thanks. Okay, one other question. Haniel Barbosa asks, what were other techniques you tried for rewriting that were not as good as the genetic algorithms? Because you mentioned that genetic didn't work well in the second case. Are there other techniques you tried?
So for the rewriting, we have, for instance, compared it to just a random search. We have also tried to come up with some more guided search, maybe some gradient descent, but unfortunately, there doesn't seem to actually be a gradient that you can specify. And similarly, for the mixed precision tuning, we've also compared it to some random search. So you basically just randomly try a number of mixed precision settings.
Okay, and one last question, since we're out of time, I'll just ask one last question regarding just-in-time compilation. So Anonymous asked, do you know of a JIT-like approach for optimizing orders? For example, if there's a function f that's called often with arguments of similar intervals, you can choose a better schedule just in time.
So that's actually a very interesting thought. We haven't thought of that, though I suspect that just for JIT, our analysis would be still a bit too slow. But if you're willing to spend a little bit more time on this, I think that should probably work.
Okay, great. I think we're out of time. Thank you so much, Eva, for your talk. Very interesting talk. And then I guess we'll move to the next session. I'll tap my hands.
Thanks.
Thank you. Okay, so now we're moving to